Okay, good evening, friends.
Good evening, sir.
Okay, I just yesterday we had a long discussion on this rotational equilibrium. I just shortened it and summarized it. Okay, I added some more diagrams to this. Yes, I think everybody understood translation equilibrium means summation Fi must be equal to 0. Okay, or the acceleration across the through the center of mass must be 0. As far as rotational equilibrium concerned, the net torque about a reference point must be 0. This implies angular momentum about that point must be 0 or constant in magnitude and direction. See, now what it means is angular momentum about that point, about the reference point. Okay, must be 0. Okay, now I'll straight away take you to this equation here. So if you see this equation here and this diagram here, it is very clear that if a body has net torque, then it will have alpha, and if the body has a net force, then it will have AC bar. Clear? If the net force is 0, AC bar is 0, and if the net torque is 0, alpha bar is 0. Clear? Now we are referencing it with respect to some point O. Now you just look at this equation. Summation Ri Fi bar means what? Supposing now try to elaborate this equation. Elaborate this equation Ri Fi bar. Okay, that means now you have this body and you have the reference point here. Okay, so at this point it is the F1 bar. At this point the force is F2 bar. At this point the force is F3 bar, and so on and so forth. So you reference these points from here. Okay, so this becomes R3 bar, okay, R1 bar and R2 bar. So summation Ri bar cross Fi bar. Okay, now this is what we call it as the torque about O, because Ri and all are reference with respect to O. I suppose all of you got this?
Yes.
Hello?
Yes, sir. Yes, sir.
So that's it. So torque at a point means from the reference point. Got it?
Yes. Yes, sir. A reference point.
Torque about the reference point.
Mm-hmm.
Okay, that is important. So you can take from a reference point and calculate all this.
Sir, we can apply the torque equation anywhere on the body, sir.
See, that is what you should apply like this.
Yes, sir.
You should apply this. I have taken this. You can take this point anywhere you want. You can take the reference point anywhere, man.
Yes, sir.
And apply this formula.
But then also the body will be in rotational equilibrium.
Okay. If it is in rotational equilibrium with respect to this point,
yes,
then if you now say this is O, now I will take this O dash, this reference point, I will shift it to O dash.
Yes, sir.
Then you will have new.
Yes, sir.
You will have new R1, R2, R3.
Okay, sir.
Then the torque about this point also must be 0.
Yes, sir.
If it is 0 here, it must be 0 here. Or if it is something here, it should be same thing here.
Okay, sir.
That is what you
Yes,
have.
sir.
That is what you have to understand. Clear? Point number 1.
Yes, sir. Yes.
Everybody clear now?
Yes, sir.
Now,
Yes.
second point. Now, if at all this torque is equal to 0,
Yes, sir.
and if there are 3 forces, then it can be proved that all these 3 forces are going to meet at some point.
Okay. Yes, sir.
Or they are concurrent. If at all this is equal to 0.
Okay.
That was the sum and substance of yesterday's discussion.
Okay.
Nothing more.
Sir, one-
Or these 3 forces are parallel to one another.
Yes, sir.
Tau O bar is equal to 0 implies all these 3 forces are concurrent,
Yes, sir.
or these 3 forces are parallel to one another. Clear? That sums up everything. Now if you have any questions, ask first.
Sir, one doubt, sir. If a body is in rotational equilibrium, any point on the body or outside the body, sir, any reference point we're taking, will the tau bar be 0, sir?
Yes, tau bar will be 0. That's what I said. If tau bar is 0 here,
Yes, sir.
then if you shift the reference point, it is 0 here also.
Okay, yes, sir.
That's what it is.
Okay.
Okay? Only thing is, you see, the axis of rotation must be on the same plane.
Yes, sir. Perpendicular.
and it should be perpendicular to the middle.
Plane and containing forces.
These two conditions must be satisfied.
Yes, sir.
That's it.
Yes.
Okay, fine. I think I summarized yesterday's this one clear. We we had lengthy discussion yesterday on that. Okay, fine. Okay, that there it goes. So I will switch over to today's class then. Okay, right. This is today's class. All right, friends. So I hope you are all ready.
Yes, sir.
Yes.
Ever ready, Baba. Okay, right. So yesterday we have discussed this problem. I think 50% of the problem we have discussed. So yesterday this was a very interesting problem. So here you find that there is a body and it's a round object, not a body, it's a round object. So its moment of inertia is gamma mr square about its center, resting on a smooth horizontal flow. A force F is shown, find the acceleration at the center of mass and angular acceleration. Quite simple. This force produces angular acceleration at the center of mass, and that will be equal to what? F divided by m, the mass of the body. Okay, and as far as the angular acceleration is concerned, this is F, this is h. So F into h minus r gives you the torque.
Yes, sir.
Now torque divided by the moment of inertia
Yes.
gives you the angular acceleration alpha. Correct?
Sir, one doubt, sir.
Yeah.
Sir, the acceleration of center of mass, sir, it is totally independent of where we apply F, sir. Like even if it passes through center of mass, it is the same acceleration.
See, again, if the force is passing through the center of mass, the transversal acceleration will be same. Correct. Wherever you apply, the transverse acceleration will not change. It will be same.
Center of mass will always have transition.
No. His question is, if you apply force here, you are getting some acceleration,
Yes, sir.
translation acceleration. Supposing you change this force from here to here,
Yes, sir.
then also it will be same, provided the direction has not changed.
Okay.
That's what it was his question. Okay?
Yes.
But the angular acceleration will depend upon the point of application of force.
Yes.
Yes, sir.
Then when we take when we are finding the acceleration center of mass, then we can write F by m, sir.
I mean, that's what we wrote here.
We can write directly.
We wrote that only now, just now I
Yes, sir.
told
Yesterday
you.
we wrote, sir. But I'm asking, sir, like.
Yeah, correct. See, no confusions whatsoever.
Yes, sir.
No confusion whatsoever. The concept of center of mass is what? If there are n number of forces acting on body,
Yes, sir.
you just take their summation, vectorial addition,
Yes.
and keep it on the center of mass. So here there is one force. Summation of F is only F.
Yes.
Keep that force there and do it,
Okay.
irrespective of where it is acting.
Okay.
That is how you have to look at it.
Yes, sir.
Sir,
See,
one doubt. Sir, now if we apply force such that it is not passing through center of mass line of action, sir, it will eventually start rotating also and translating also.
See, we'll come to that. Now, I hope you got this point right here.
Yes, sir.
You got this point right. Got it? Now, you see, right now what we have seen is, at the moment this force is applied, it will have both. Right? And the floor is smooth.
Yes, sir.
Hello?
Yes,
Yes,
sir.
sir. Yes, sir.
Now, that is why I gave you the homework yesterday. What homework I gave you? So, if there is friction, did you attempt to make that homework, solve that homework?
Yes, sir.
No answer from anyone.
I didn't take any.
Okay, so here you see, we got this final answer yesterday here. F into h minus alpha is so and so. If h is equal to r, alpha is equal to 0, no turn effect. I think till this point all of us got. And then I gave you this homework. What is the homework? If the surface is rough, to prevent some slipping, determine the following quantities. Which quantities? The x component of the acceleration of the center of mass, the y component of the center of mass, alpha, and the frictional force F. Got it? Hello?
Yes, sir.
Yes, sir.
Yes, Tishan?
Yes, sir.
You know question, Kerry? So now we will analyze this situation. Okay, we will analyze this situation. Okay, that's important. So now what we do, we have this body, we have the surface. So there is friction here. But remember, you can use both. You can use both. Mus and uk. Okay?
Yes, sir.
Both are there. Okay? That's it. So now, first of all, we have seen that this force is applied. This will have this acceleration AC of x, and it is having alpha like this. Yeah, just got it from the previous thing. So under this circumstance, what happens? This point is trying to move like this. Correct? So therefore, we will consider that there is frictional force in this direction.
Yes, yes.
Okay, there is friction. We'll start with this equation.
Okay, sir.
We'll start with this equation.
Yes, sir.
Okay. So now with this one, we will develop the math model. With this, we will develop the math model. So now, if you take this into account, then what will be AC of x equal to? It will be equal to
Alpha.
hey f plus
F plus F
f
by
divided by u.
Yes, sir.
Yes,
Yes, sir.
Point number one.
Ah, sir.
Okay, this is the first thing.
Yes, sir.
So you can call this as the first equation.
Yes.
Yes, sir.
Now, yes, come to the rotational. Okay, so this is it.
F.
So what will this be now?
Capital.
Due to this, yes, due to capital F into h minus r.
Yes, sir.
So this torque will be like this.
Yes.
And due to this, okay, minus F into r will be anticlockwise.
Yes, sir.
What is this? This is the net torque.
Yes, yes, sir.
Yes, sir.
Yes, sir.
Okay, and this net torque will be equal to, they are given the inertia, right?
Gamma alpha.
So gamma m r square, they are given,
Yes.
into alpha,
Yes.
okay, into alpha, right? Gives you the second equation.
Yes.
Yes,
So this is equation number 2. Okay, and of course, AC of y is equal to 0.
yes, sir.
Okay, there is no acceleration this. So now they have asked us in this problem to calculate this one, and this one. So one quantity is already calculated. Okay, but they have not given this. See, they have only given this quantity, they have only given this quantity, they have only given this quantity. They have not given smallest. And of course, they are given these quantities.
Yes.
Right? Understood all of you?
Yes.
So now we have to now, okay, can we get one more equation? AC of x
That should be equal to alpha and
alpha into r.
yes,
Yes, sir.
That should be equal to alpha into r.
alpha and
So we can get one more equation. Okay, so we can get equation number 1, equation number 2, and equation number 3.
Yes.
Right. So now, first of all, we will try to eliminate f.
Yes, sir.
We will try to eliminate.
Sir, the second equation, so that AC equals alpha and r, so that is true if the body is rolling.
Yeah, if the body is rolling only.
Yeah.
Correct.
Do you
If the no, they are not. No, that's what they are only told. It is friction. This is friction.
It's not slipping the
No.
Friction.
They are told if there is friction. See, don't get it wrong, right? If the surface is rough enough to prevent slipping,
Yes, sir.
and it is sufficiently rough.
Okay. Yes, sir.
Okay, then what are these so and so?
Yes, sir.
So, wow, this is right. Okay, this is the only condition possible, provided it is not, it is rolling without slipping. So we don't know whether it is it, so therefore we cannot write this equation.
Okay, sir. Yes, sir.
Got it?
Yes, sir.
If it is rolling without slipping only, this condition will be there.
Yes, sir.
Otherwise, this condition cannot be there.
Okay, sir.
See, if the body is getting dragged, then we know it will not.
Sufficient time. Yes, sir.
So these two, okay. So from these two equations, we can see from this equation number 1, we can get it as F plus F is equal to M into AC. Okay.
Yes, sir.
Okay. Now in the second, so you can now substitute in the second equation here. There is r square. I can pull that r down here. I can write here f into h minus r divided by r.
That will be negative.
Okay. Minus f is equal to this equation. Okay. I am pulling one r out here.
So
M gamma m r alpha.
that will be a negative acid, sir. Our that it is in clockwise direction of sir f into h minus r. So it will be in the minus k direction, sir.
That's okay. That's okay. Let's see.
So we didn't take the minus that one as
No. I have taken this plus and this minus. No. I have taken 1 plus and 1 minus. No.
Okay, sir. Alpha I have taken positive, sir, so capital F was
Okay. Fine. That should not be a problem.
okay. Yes.
Now, if I add these two equations, f will get eliminated.
Okay.
Yes.
I will simply eliminate f here.
Yes.
So I will get here. Okay. F. Okay. This f plus f into h minus r divided by r. Okay. Will be equal to. So here m is common. Right? M is common here, and we get here AC of x plus alpha
Gamma.
gamma r. Okay?
Yes.
So we get this condition.
So then also, sir, like we will not.
Wait, we'll have to.
That f at least one of them, sir, the signs will change in the second equation, sir. F by r into h minus r, sir. If you are considering clockwise is positive, sir, then anti-clockwise should be negative, sir. So it should be minus f or your
ಇಲ್ಲಿ ಬರ್ತಿದ್ದೀನ ಆಲ್ರೆಡಿ ಮೈನಸ್ ಸೈನ್ ತಗೊಂಡಿದ್ದೀನಲ್ಲ ಮೈನಸ್ ಎಫ್ ಯಾಕೆ ತಗೊಂಡೇ ಇದೆ why did I take minus because it is anti-clockwise.
Okay, sir.
I have already taken that into consideration.
Yes, sir.
Okay.
Yes, sir. Yes.
Okay. Now further, can you do some more work on this and get one good mathematical model so that you can talk about the frictional force here.
Sir, we'll have to consider physics. So, like, if it is flipping, sir, then
That's all. All the considerations you have to take into consideration. This till this equation.
So they are given friction prevents slipping, sir. So we can write A is equal to alpha.
At present, wait. At present, we are just holding it. Because you see, it should roll without slipping.
Sir,
Yes.
they are
So
given
it's equal to alpha.
it's sufficient to prevent slipping, and you can use that equation. If it's not slipping, means it's rolling, sir. Like the distance covered in one
Yes.
rotation will be 2 pi r, sir. So we can take that.
If that is the condition, we can take.
Yes.
If that is the condition, we can take.
yes, sir.
Yes.
So nothing wrong. See, we can always include that at any point of time.
Yes, sir.
But now,
Okay, sir.
see, now we have just generalized this equations like this. Okay. Now our next task is what we have got to do it here. So if that condition, if you say it is not slipping, then you can jolly well write ACX is equal to alpha. So you can straight away write here alpha r here, and you can get 1 into gamma. Understand? So if you take this condition there, and you can simply write here, because they have already given there, the friction is sufficient to prevent slipping. Then you can use that condition there, and you can ACX, you can write it as alpha r. So m into alpha r, you can take it outside, and you get 1 plus gamma inside.
Yes.
Yes, sir.
And MACX is
Okay.
alpha and ACX.
You can
Easily, you can write that also.
Yes.
You can write that also. You can write this also. Okay. So from this, can we write for f here F here will be what? F into bracket 1 plus H minus R by R.
So, HY.
Right?
Yes.
This is equal to M alpha R 1 plus 1. So the simplification of this. Okay. So I can now straight away write F is equal to. You can write F is equal to. Okay. This R also can be taken up there. So I can write it M alpha R square into 1 plus gamma. So this R goes there, R minus R, and H will come out. Correct? Am I doing justice here? Hello, please help me.
What you are doing is correct.
The same.
I got this now? Correct now? Huh. So now if F is this, then what about small f? What about the small f? So the small f will be equal to what? Small f will be equal to, see here, from this equation. From this equation, in MAC, small f will be equal to alpha R minus capital F from this equation.
Yes, sir.
M into AC is alpha R. Oh no, M alpha R. Correct? M alpha R minus F. Hello?
Yes. Yes.
So this one, if I expand, M alpha R minus, instead of F, write all this. M alpha R square 1 plus gamma divided by H. So this one M alpha R again take it common.
1 minus.
So this will become, I can this will become 1 minus R into 1 plus gamma by H.
Yes, sir.
Correct?
Yes.
Yes, sir. Yes.
Small f, sir.
Small f is. Okay? So now, there are some conditions. So if those conditions are satisfied, okay, then we can comment on the friction. We can comment on the friction. What type of friction is there? Anyway, I have better equations to get going with that. I hope all of you understood this now.
Yes.
This analysis, all of you understood?
Sir, one thing, sir. There, F, sir, you firstly assume no, sir, like it's in the direction we have assumed.
We have assumed.
Yeah.
We shall see. You will get better clarity. You will get better clarity into this idea. So you see here, if the surface is rough enough to prevent slipping, Ax came alpha F. Okay. Now F is less than or equal to mu mg. That is static friction. It has not yet reached the static friction. Understand? Sufficient friction. Since no slip between the contacts. So VCM is equal to omega r. So ACM is equal to alpha, no slip at the contact. Fine. So this is the diagram. Fine. So F plus F is equal to MACM, MACY is equal to 0. Now, okay, we also got the same equation. Tau C is equal to so and so.
Yes, sir. Yes, sir.
Okay, and we got this equation number 1 and equation number 2. And solving, we get this. We had to arrange those equations like this. So if you arrange this equation like this, so this capital ACM is so and so, F is equal to so and so.
Yes, sir.
Okay, in fact, F was already given. I was writing there F.
Okay,
F is already given. Now you can comment on this. Okay, if H is equal to gamma plus 1 into R, then F is equal to 0. So you see here, the friction will depend upon the position.
Position, yes, sir.
Yes, sir.
And if H is greater than gamma 1 plus R,
F is positive, yes, sir.
okay, then F is positive and it will act to the right.
Right.
Yes, sir.
Yes, sir. Yes, sir.
And if H is less than gamma 1 plus R,
It is
then
negative.
F is negative and acts to the left.
Yes, sir.
Yes, sir.
You got your answer, Mr. Srijan?
Sir.
Yes, sir.
See, it is so interesting. Okay, and in fact, this is good. I just have a look at it and just visualize. This is quite possible. So,
Yes, sir.
Yes, sir.
okay.
Ah, sir.
Got it, all of you? Huh?
Yes, sir.
You want to make a note of it? You can make a note of it.
Yes, sir. Yes, sir.
Okay, friends?
Yes, sir.
Very, very interesting. Aram, sir. Okay, so here you see in these problems, again, wherever we have encountered friction, we did have to say, okay, let us assume like this and do it at many situations here too, but we get wonderful abstraction here, and that should give us a good clarity on what's happening. Okay, shall I proceed, friends?
Yes, sir.
Yes, sir.